In the previous video, we have finished chapter 3 on the transport layer, and start from today. Let's keep learn chapter 4, network layer. And for this chapter, we will cover all the high-level details about a network layer. And first, let's see the introduction of a network layer. So the network layer will transport or forward the segment from the sending side to the receiving side. And on the sending side, uh, the network layer will add a network header combined with the segments to get a datagram and start or ready to send it out. And on the receiving side, the network layer will deliver the segments to the transport layer after extracting the segments from the datagrams. And then the network layer protocols is not only implemented on the end systems or these devices, actually it's also um, integrated in the network core part, which is in the router. Therefore, for except the switches, all other devices will be integrated with the network layer. And router examines header fields in all IP datagrams passing through it. So that means the router will open up each datagram's header field to see the IP address, destination IP address inside there, and to decide which path this packet or this datagram should take and forward it to. And also you can see here, not only the end devices implement the network layer, and also all the routers, they will implement the network layer function. And then actually we in the chapter 1, if I remember correctly, we already talked about the two key functions implemented on the network layer, which are forwarding and the routing. For the datagram forwarding is a move packets from router's input to appropriate router output. And for the other one, the routing is just determining the route taken by the packets from the source to the destination. Uh, in order for us to better understand the forwarding and the routing, let's give you guys examples. Suppose you have a trip from Oxford to New York, and you will ask your trip agent to make a plan for you, and then for that plan we call it a routing. For example, your trip agent will tell you, okay, you can take the car or drive a car from Oxford to Memphis first, and then from Memphis airport you can take the airplane and fly to New York. So that's the entire plan or the routing for your trip from Oxford to New York. For the forwarding, actually, it's just do each step specifically. For example, in Oxford, which car you can drive or you can take to the Memphis, and from Memphis International Airport, which airplane you can take and fly to New York. So that's the same thing or the same example like the two functions implemented on the network layer, which are forwarding and routing. And also, I bet you guys is familiar with this slides because we already talked about these slides in chapter 1, if I remember correctly. For actually in each router, there is a forwarding table which is calculated by a routing algorithm, and in in the middle or the last part of this chapter, we will talk about the different routing algorithms. And so right now, you don't need to worry about how they can calculate the each content or pairs inside the local forwarding table through the routing algorithm, or how the routing algorithm works. Actually, you don't need to worry about it right now. Um, so you just know we will generate the content inside the local forwarding table through the routing algorithms. And actually, in the local forwarding table, there are two columns. One is a header value. Another one is output link. Actually, the header value just represent the IP address in reality. But here's, since we just to serve a illustration purpose, so we don't want to add a 32-bit IP address in the header value field. So we just use a 4-bit values to represent the header value, which is the IP address in reality. And suppose here we have a packet or datagrams around this router, and then the router will open the header of these packets to see the destination IP address, which is 0111, actually this value, and take this value to search or look up through the local forwarding table to see which output link this packet should take. And then after we search through the table, we found that this line is our answer. So that means this packet should take output link 2. And then the router will use the forwarding function to forward this packets to output link 2, which is through this link to this router. And then when this packet arrives this router, and it will do the same thing, exactly the same thing as they did in this router. They will open the headers and take the destination IP address, search through the local forwarding table, and get output link and forward to the next router or to the destination until this packet arrives the destination. This entire routing and forwarding things will be terminated. Then let's see the network service model here has a question. So what service model for a channel transporting datagrams from sender to receiver? Actually, this question is asking or the expectation from the upper layer. The upper layer means for the application layer and the transport layer. So what kind of a service model they are expected from the network layer? First, let's see their expectation for the individual datagrams. They expect um, they expect the network layer can provide a guaranteed delivery. So that means each single datagram can be received by the destination. Another one is guaranteed delivery with less than 40 milliseconds delay. So that means they have a requirement not only to receive the datagrams without any packet lossing, and also they expect uh, a delay restriction, which means 40 milliseconds. And also for flow of datagrams, their expectation is for these datagrams, they must arrive in order. Here's in order datagram delivery. And also they guarantee the minimum bandwidth to flow. For this one, which means if the network layer can be provided by specific um, or minimum bandwidth, the packet cannot be lost on the way. they can be delivered to the destination for sure. Another one is restriction on changes in interpacket spacing. So for this one means um, the granularity or the time interval for each two packets sended out from the sending side should be equal to the granularity or time interval received on the receiver side or destination side. But let's see the reality is, so the service model provided by the network layer, which is the best effort. So we already talked about the best. What's the meaning of a best effort? It just do the best for the network layer. Actually, it cannot guarantee anything. So that means the network layer cannot guarantee the bandwidth, the packet loss, the order, timing, and even the congestion feedback. The routers cannot provide it to the sender because the packet loss will be inferred through the packet loss, as we already mentioned in the TCP protocol. Then let's continue to talk about the more details inside a router. So as we already talked about that, there are two key router functions, which are routing and forwarding for each router. And then let's see the architecture for each router. So the routing processor, which is like the CPU to run the routing algorithms to generate the result of a local forwarding table, which is on this level above this dash line. Actually, these routing functions, they are implemented on the software layer or level. But for the forwarding function is implemented on the hardware level, which is under this dash line. And after the routing processor calculate or run the routing functions or routing algorithms, it will pass or deliver the copy of the local forwarding table to each router input port. Therefore, for each router input port will hold a copy, which is here, a copy of the local forwarding table content. And on the other side is the router output ports. So they will forward the packets or the datagrams to the next hop. And in the middle is the high-speed switching fabric. For this part, uh, they will get or receive the packets from these router input ports and deliver them to the router output ports. So all these input ports, they will share the function of this high-speed switching fabric. So that means the high-speed switching fabric will serve all the router input ports and also provide the input for all the router output ports. And then let's see the closer for the input port functions. For each input port, it includes three parts. The first part, this box, we call it line termination, which is implemented on the physical layer. So for this part, the function of this box is to decide where is the end of the package or the end of the datagram. The second box is a link layer protocol. So when we talk about the link layer, which is chapter 5, we will learn more details about how the link layer works. And for the last box, for this box, the main function is do the decentralized switching. Actually, for this one, is the location, the local forwarding table stored. And also, there's a buffer in this box. Why we need to have this kind of decentralized switching? Because if we don't have this box, so you can imagine when there's a packet around this input port, it must send a request to the routing processor to get the information, output link information from the local forwarding table. And then the routing processor will give a response back to this input port. And then this input port can use the switch fabric to chosen which output link this packet should take and do the forwarding function to move it to the next hop. However, since we have this box, it already cache or already store a local forwarding table. That means when the packet arrives this input port, uh, it can directly search through this local forwarding table to get the output link information and directly forward these packets to the switch fabric and to the output link. So that means um, it doesn't need to bother the routing processors. So that means it just released the burden of the routing processor. And also the goal for this decentralized switching is complete input port processing at a line speed. So that means the line speed is the higher limit of the link, higher speed limit of the link. They will use that maximum speed to transfer the packets. And for the queuing, means, as we already mentioned, for each box in the input port function, there is a buffer. So that means if the input or the packet arriving speed is faster than the switch fabric speed, that means there's more packets will accumulate on or in this box buffer. That's the queuing. So if datagrams arrive faster than the forwarding rate into the switch fabric, they will temporarily store on this buffer. And then I see this destination-based forwarding. For this part, we need to, because here each destination address, which is the IP address, and each one is a 32-bit 32-bit integers or strings. So we need to consider it carefully because in total there are 4 billions of IP address for the entire domain. So that means we cannot put all the records, put all these 4 billion IP address in each forwarding table. If you want to search as we output link result through this table, suppose for each record it will take 1 millisecond. So that means you will take 4 billion milliseconds time on average to get the result from this forwarding table. And also you can imagine how large the delay will be. Therefore, the solution they used is to make a range for each link interface or output link. For example, from this IP address all the way to this IP address, in between all these packets, if their destination IP address belongs to this range, they will take output link 0. so on and so forth. For this range, they will take output link 1, and for this one, they will take output link 2. However, due to the historical reason, for some IP address, even though they belongs to uh, a range from this 3 range, however, they will take um, exception output link, which is output link 3. So that means so that means um, due to the historical problems, we cannot divide the range on the forwarding table very nicely. If that's the case, so what happens if the range don't divide up so nicely? So what should we do? How can we handle these exceptions? Actually, the engineers, they are so smart. So the solution they gave us is a longest prefix matching, which is when looking for a forwarding table entry for given destination address, they will use the longest address prefix that matches destination address. For example, here, this give us a table, and for each one, it's just a prefix for that range. For example, this one is a 11001000 and 00010111 and 00010. For this one, it will take a output link 0. However, for this one, will take 1. And for this one, actually this one is the subdomain of this one. However, they will take a different output links. And also here has otherwise. So let's do some examples for this one. So which output link you think the IP address will take, or the output link this IP address will take? So actually for this one, after you do this matching, you will see the first one, this one, is the longest address prefix. This IP address can be matched. So that means for this IP address, it will take output link 0. Then I see the second one, the second IP address, this one. Someone maybe think, okay, let's do the longest address prefix matching. So probably this one is the answer. But actually, if you keep searching or keep doing the matching, you will see the second one, it can satisfy the longest address prefix matching. Therefore, the result or the answer for the second IP address, it will take output link 1 to do the forwarding. Then let's see the switching fabrics. It will transfer the packet from input buffer to appropriate output buffer. And also for the switching rate, the rate is at which packets can be transferred from inputs to its outputs, and how fast they can transfer over the switch fabric. And also, there are 3 types of switching fabrics. One is the memory, the second one is the bus, the third one is a crossbar. Then let's learn them one by one. First, let's see the switching while or through a memory. Actually, this switching through memory is the first generation routers. For these routers, they are actually they are designed or implemented actually through the traditional computers. So their switching is under the direct control of CPU. So the packet copied to system memory first, and then the speed is limited by the memory bandwidth. because for each packet, it must take two bus crossing um, to get into the memory and then get out from the memory to the output port. Then let's see this one. So for each packet arrived on this router, they when they get onto the memory, they must do it one by one. When they arrive the memory, they need to do it one by one. And the same as when they leave the memory, it still do it one by one. So they cannot do it simultaneously. And also, there's no local forwarding table copies stored in each input port. So that means each input port, after they receive a packet, they must forward it to the routing processor and also through the memory to get to check or do the matching from the local forwarding table and then get the output link for each packet and out of the memory then deliver to the output port. So the problem is all the packets they must share the same bus. Therefore, it highly decreases the speed, the processing speed of this kind of router. The second one is switching through a bus. So for this one, the datagram from input port memory to output port memory through a shared bus. Here there is a bus contention. It's a switching speed limited by the bus bandwidth. And also for this one, it's the same as the previous one, as the memory one, because all the packets they must share the same bus. However, the advantage for this bus switching is for each input port, it has a copy of the local forwarding table. So that means each packet around the input port, they can check the output link locally, and then they just use the shared bus to forward the packets to the output port. So that means each packet they don't need to bother the routing processors and give give the burden to the routing processors. So that's the advantage of switching via a bus version. Here we have example an example of routers. There is a 32 gigabps bus, Cisco's 5600, which is an example of a switching through a bus, which is a sufficient speed for access and enterprise routers. Let's see the third type, which is a switching through an interconnection network. So for this one, it can overcome the limitation of bus switching. First, let's see the um, switch fabric part of this version. Actually, it's here. We can see it. It's just like a mesh, or we call it interconnected and interconnection network. So for this one, why it can overcome the bus switching? Because the different input packets, if when they destinate to a different output port, so actually they can do the transmission in parallel or simultaneously. However, if different input packets they destinated to a same output port, it cannot take the benefit for this kind of structure. But in total performance or the average performance, the switching through the interconnection network is better than the bus switching. Here we have an example which is Cisco 12000. It can reach a 60 gigabps throughput through the interconnection network. Then let's see the output ports. So the output ports, when we see this figure, it's just a inverse order when we compare it with the input ports. So first, for the first box on the left is the datagram buffer. So when the packets arrive in this output port, it will first temporarily stored on the buffer of this box. And then the second box is the link layer protocol. So the packets will forward to the next layer, which is the link layer, and through this box. And for the last box, it's a line termination. It will serve the same function as in input port, which can decide where is the end of the packets or the message. And this line and this box is implemented on the physical layer. And also here there are scheduling display. So which choose among queued datagrams for transmission. Actually, it will do order. So which datagram can be transferred to the next hop first. So very commonly, the scheduling they used in router is the first come, first serve. However, for some specific routers, they will use another way. We call it weighted fair queuing. So that means for each datagram will be assigned a weight. And based on the weight, the router can decide which datagram can be forwarded to the next hop first. And for the output port queuing, for this part is if we see from this line, so the switch fabric arriving speed to the output port is faster than the output speed. Then the packets or the datagrams will be temporarily stored on this on the buffer of this output port. So if the buffer get filled up, it can the packets can be experience a packet delay or a packet late or packet loss due to the output port buffer overflow. For the input port queuing is the fabric or switch fabric transfer speed is slower than the input ports combined. So that means all the input ports speed, transfer speed, add them together to compare with the fabric speed to see which one is larger. If the combined input port speed is faster than the fabric speed, so that means the queuing will be experienced on the input queue, which is along this line. And also, the queuing delay and the packet loss will be happened when the input buffer get overflow. And there's another reason can cause the input port queuing. We call the head of the line blocking. Here we short it for HOL blocking, which means the queued datagram at the front of queue prevents others in queue from moving forward. So that means, let's see our example. Suppose this red color datagrams and this red color datagrams, both of them, they are ready to forward to the same destination output port. However, if that's the case, only one datagram can be forwarded or temporarily stored on the buffer first. So on the top, this this red datagrams is so lucky, so it can um, load it on the output buffer first. So for the lower one, for this one, it must wait for the for this one get loaded on the output buffer. However, the blue packets here, even though we know this buffer is clear, there's no any packets use this buffer or occupied or temporarily stored on this buffer. However, this green packets must waiting for this red one loaded first, and then this green one can be transferred to its destination. So that means this green packets will experience HOL blocking as well, because the front datagrams experience a queuing delay.